Alrighty, this is the third in a series of 4 podcasts for Chapter 4. We're going to talk about oxidation reduction reactions, commonly referred to as redox reactions. I don't know why they're called oxidation reduction, but then you call them redox. Doesn't make sense to me. But anyway. Alright, oxidation occurs when an atom loses, or an ion loses electrons. Reduction occurs when an atom or ion gains electrons. In order to have one, you must have the other. Now, it's important to remember what oxidation and reduction stand for. We have two, memorization aids, I guess. Oil rig is one. Oxidation is losing electrons. Reduction is gaining electrons. You can also use Leo says Gur. Losing electrons is oxidation, gaining electrons is reduction. Okay, and if you think about it, what happens to the oxidation number if you gain electrons? If you gain an electron, it becomes more negative. Your oxidation number of your ion or your element is reduced by 1 because you're adding a negative. Alright, so what we need to do is learn how to use oxidation numbers. Okay, we're going to assign an oxidation number to each element in a neutral compound or a charged entity. Elements, if they are in their elemental form, are considered to have an oxidation number of 0. Oxidation number of a monatomic ion is the same as its charge. Okay, let's do a couple examples here. Cl2, that's how it exists as an ion. It would have an oxidation number of 0. Any metal, such as sodium, oxidation number of 0. Oxidation number of a monatomic ion, for example, the sodium ion has an oxidation number of +1. The chloride ion has an oxidation number of -1. Nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. And that actually includes things like chlorine. Oxidation number oxygen typically is -2, except in the peroxide ion, which it has an oxidation number of -1. Peroxide ion is O2 minus. So each oxygen atom has a -1 charge. Hydrogen is -1 when bonded to a metal, +1 when bonded to a nonmetal. Nonmetals tend to have negative oxidation numbers, although some are positive. Things to remember about nonmetals: fluorine, most electronegative element, always has an oxidation number of -1. Always. Other halogens usually have an oxidation number of -1, but they can also have positive oxidation numbers, usually when they are combined with oxygen. Things combined with oxygen and forming a anion are known as oxyanions. An example would be the hypochlorite ion. Nope, that's the hypochlorite ion. Sorry. Some of the oxidation numbers in the neutral is 0. If the overall compound or polyatomic ion has a charge, the sum of the oxidation numbers have to equal the charge on the ion. Let's look at some displacement reactions.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
Okay, and then let's look at the second video, part 2.
When a zinc rod is immersed in dilute acid solution, hydrogen gas is evolved and zinc ions form in the solution. The solvated hydrogen ion is represented as a hydronium ion, H3O+. In this reaction, zinc is oxidized and hydrogen ion is reduced. When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation-reduction reaction occurs. In this reaction, zinc is again oxidized. Now, however, copper 2+ ion is reduced to copper metal. In the two examples we have seen, zinc is oxidized. Because it causes the reduction of other substances, zinc is said to be a reducing agent. The substances that are reduced in these reactions, hydrogen ion or copper +2 ion, are oxidizing agents towards zinc.
Okay, so keeping that in mind, a reducing agent undergoes oxidation. An oxidizing agent actually undergoes reduction. And yeah, you need to keep that straight. Don't know why it goes back in time. Okay. So in a displacement reaction, and what we've called these before really are, we refer to them as single replacement or single displacement reactions. Ions are going to oxidize an element. The ions themselves are reduced. And we just saw that. Okay, in the reaction I have something like a, actually I do have a silver nitrate solution, and copper metal. Uh-oh. Get the pen working again. Sorry, I do have issues with the pen. It's still not there. Hang on. Oh, dip. Okay. I have the silver ion from the silver nitrate, so you notice that we're doing a net ionic equation. Okay, and the copper solid, oxidation number of 0 since it's the element. Each of those silver has an oxidation number of +1. Reaction occurs, and it's really just electrons being transferred from the copper to the silver ion. And then I get a copper ion +2 and 2 silver atoms forming a deposit, and hopefully in that test tube right there you can see the fuzzy stuff forming, which is the silver. Okay. This reaction does not go in the reverse. Okay, the reactivity of the copper ion or the reactivity of the silver, depending on how you want to look at it, is not great enough to cause the reaction to go in the reverse. So single replacements really only happen in one direction. You may be asking yourself, well, how do you tell? And most of you should probably already know the answer. And that is really by looking at an activity series. Okay. This activity series is in decreasing oxidation reaction. Oxidation is losing. Okay. So the most reactive is going to be this lithium. Okay. And of all of these equations, this equation is likely to happen the most, I guess is one way to say it. What you want to make sure you realize, and the AP reference sheets, sometimes they flip the orders of these series. And usually what you'll be given is actually not an activity series, but a electromotive series, and we'll actually have voltages, and we'll get to that way in the future. Okay, but you've got to be aware of what order the table is given to you and what it means, because sometimes they will flip it. Okay. We'll do some problems on these in class. We're going to finish looking at the redox chemistry of tin and zinc. Okay, or at least I thought I was. Nope. Oh, sorry, did you guys see that? And I didn't see it through there for a minute. All right, redox chemistry of tin and zinc. Sorry. There we go.
Finally, some acidified tin 2 chloride solution is poured onto a piece of granulated zinc. Again, we notice an almost immediate displacement. In this case, we are getting some bubbles of hydrogen produced as well, because there is acid in the tin chloride solution. However, the main thing to notice is that the piece of granulated zinc is becoming coated with fine crystals of tin. After some time, the tin crystals grow out as needles from the surface of the zinc. These are pointed needles of tin on the surface of zinc.
Alrighty, and that's it for this third podcast. I'll be making a fourth talking about molarity and titrations.